Hello, I'm Joe Hamaker, and in this presentation, I'll be discussing estimating the cost of technology advancement for space projects. Now, first, a little bit about me. I'm the Director of DoD and NASA programs at Gallerath Federal. Formerly, I directed cost at NASA, and I have over 40 years of experience with cost estimating and analysis. My email address is at the bottom of the chart, jhamaker@gallerath.com. Now, first thing, this presentation concerns the cost of technology advancement, which ideally occurs prior to the initiation of full-scale development for the most part. So in other words, the cost of schedule advancing technologies along the NASA technology readiness level scale, which is shown there on the chart. I'm sure most of you are familiar with the NASA TRL scale, running from TRL1 to TRL9. Now, there's another and separate frequent cost topic regarding TRLs, and that is, what is the penalty for entering full-scale development, either on purpose or unknowingly, with technology that's not yet mature? So I have another presentation on that subject, and that one is titled Estimating the Cost Penalty of Entering Full-Scale Development with Immature Technology. This presentation will provide you with a simple parametric tool that can estimate the cost and schedule of advancing technologies along the NASA TRL scale. The tool will be in the form of a CER, cost estimating relationship, and an SER, schedule estimating relationship. And the basis of the CER and SER is a set of NASA cost and schedule estimates for some TRL advancement projects. Now, basing a model on estimates as opposed to actuals is less than ideal. But this model is based on some TRL projects from a few years ago, and since then, those projects have presumably advanced and historical data can now be obtained, and the model can be based on actuals as opposed to estimates. So along that line, we've been recently discussing this with NASA about getting the access to that data and using actuals as opposed to estimates, and I may be updating this model in 2021. So the NASA space technology portfolio that I used is conveniently found in a NASA Inspector General report titled NASA's Efforts to Manage its Space Technology Portfolio. You can Google that IG report and find the database that I'm using here in this analysis. So in that report, they discussed each of the technologies with charts like the one on the right. So it includes a description of the technology advancement project in a narrative paragraph. It includes NASA's estimated cost. Now, in this case, for example, this is a deep space optical communication. In this case, they had an estimate of $10.8 million for that project, a scheduled estimate of 72 months, and they were trying to get from the then existing TRL2 to a TRL6. Now, I wanted to add a complexity rating to this database because I feel that each of the technologies potentially has a different level of complexity. So I used a scale from 1 to 5, where 1 corresponds to an easy technology and 5 corresponds to a difficult technology. And I personally rated each of the 50 technology projects on that scale. Now, if we proceed with improving this work, as I previously mentioned, I'll probably also improve the complexity rating scale. The example one shown on the bottom of this chart is one from Chicago State University, something like that one perhaps. And also I'd like to be able to use NASA subject matter experts to rate the complexities. Here's the database from the IG report in the form of an Excel table. The name of the technology is given in the second column there. The TRL start is given in the TRL start column. The TRL goal is given in the TRL end column. The estimated schedule and cost are given in the next two columns. And then my complexity estimate of each of the technologies is shown. And finally, I'm calculating the final column, the TRL delta, which is simply the delta between the difference between the TRL end and the TRL start, which depicts how many TRL steps they're trying to get through for the given budget and schedule. So some statistics from this database: the average TRL advancement is 3 TRL steps. The average cost is $25 million. The average schedule is 59 months, and the average complexity rating is 3, which is a happy outcome because I'm using a scale from 1 to 5. And statistically, you'd like your scale to be centered on the mean, and in this case, it is. So I'm going to fast forward through some regression analysis here and spare you that and show you the results, the final results that came out of the regression analysis. So the best cost estimating relationship and schedule estimating relationship that I was able to obtain from the database is shown here. They both the SER and the CER use TRL delta and complexity as the two independent variables. Now let's look at the cost equation in the box on the left first. You can see the regression equation there, and that's in logarithm terms. The p-values are shown there for the two variables, TRL delta and complexity. Normally, you'd like a p-value of 0.05 or lower. Sometimes 0.1 or lower can be acceptable. In this case, it's a little above that. My p-value for TRL delta is 0.115. So that's a little higher than what you'd like. But on the other hand, I really need to have TRL delta in the cost model. And a p-value of 0.115 is not that bad. So I elected to leave the variable in. The complexity p-value at 0 is fine, and the R-squared is good at 81.2%. The box on the right shows the estimating relationship for the schedule. And again, it uses the variables TRL delta and complexity. In this case, all the p-values are fine, but the R-squared at 31.1% is quite a bit less than what you'd like. Now, this is not unusual with schedule estimating relationships because the span of the data is usually pretty low variability compared to cost, for example. The regression analysis has a little trouble separating out the signal to noise. And so we often see R-squareds around that, no better than 30 or 40 or 50%. When I exercise these two equations back against their own database, I'm showing the results of that in the bullets at the bottom of the chart. The average cost error was a -5%, but that's with positives and negatives, positive and negative errors canceling each other out. So if you take the absolute value of all those errors, the absolute value cost error is 32%. The average schedule error was 32%. And when you absolute value those deviations, it's 44%. So those are acceptable, not great, but they're acceptable in my opinion. Now, if you don't like the pesky logarithm forms of these equations, you can change them back to a power curve. I'll show you how to do that on the very bottom of the chart as an example for the cost equation. So the cost equation can algebraically be rewritten as cost equals E raised to the coefficient we had there, the constant we had there of -0.935. Then the coefficient on the TRL delta becomes the B value or slope, and we're going for a y equals ax to the b equation form here. So the 0.217 coefficient on the logarithm term for TRL delta becomes the slope of 0.217. Same thing for complexity. The coefficient of 3.04 we had on the logarithm complexity term becomes the b value of 3.04. So the final form of the equation is given there, 0.3926, TRL delta raised to the 0.217, and complexity raised to the 3.04. Now you can algebraically change the SER logarithm equation to be a power equation as well, if you prefer that. So in conclusion, the CER and SER on the previous chart seem to provide reasonable cost and schedule estimates of the TRL advancement projects that I had in the database, although the model is based on estimates, not actuals. And as I've already mentioned, we're in discussions with NASA about using actual cost and schedule data. And I may be updating this model sometime in 2021 and hopefully have an improved model. So final word, Gallup is a 75-person company dedicated to providing our customers with best practice cost analysis. Some of our skill sets I've listed there. I'll let you scan through that yourself. Our web page is noted at the bottom of the chart. And again, my email address is given at the bottom of the chart, jhammaker@gallarath.com. Thank you very much.